All right, evening, everybody. One more time. Let's get started. Before we start, I guess a couple of points I wanted to go over regarding the scheduling. So I got your schedules, overall, I guess, semester schedules for every section a couple of days ago. The schedule looks extremely busy for everybody. There's very little, I guess, well, not just very little, there's barely any free time throughout the week where we could have, um, no sections having any classes for at least even 2 hours, let alone 3 hours. There's I analyzed every single hour of the day, basically of the week. There's always at least one or two sections having classes. So for that reason, the only time that fits everybody, or almost everybody, it's not even perfectly everybody, but it's pretty good, is Friday, 7:30 p.m. So what we have is nobody has any classes except for section 710, which is only not the whole maybe section. It's hard for me to tell from the information that I have, but seven people, looks like, from section 710 have a class until 8:20 on Friday. So these people won't be able to join us until like 1 hour into the lecture, which is, like I said earlier last week, which is to be expected considering how many students we got. Um, Another thing is we got, and that's what I wanted to ask you guys, we got section 7 on no, I think 7-Eleven actually has us with seven people finishing at 8 p.m., 8:30 p.m. So, section 710 has the class until 7:20, and that's about 20 people. So I was wondering if we have anybody today in the audience from section 710. Let me know if we do, because I wanted to ask you guys what kind of class you have, whether it's an online class, whether it's a lecture in the college, or whether it's a lab. Because for you, let me just double check here. Yeah, it is section 710, 21 people, 21 student has some sort of a class until 7:20. So do we have anybody from that section 710 today? Because if it's an online class, it's one thing. If it's a lab in college, it's a different thing. As far as the lecture attendance, it's okay, I guess. You can always watch the file after, but as far as the tests, which we will have three times a semester, um, it's going to be a little bit challenging, could be challenging, de depending on whether people have to commute or they actually are in college. Okay, so we got actually someone. So Cecilia, thank you. So micro project until 7:20. So that means you guys are in college at that time. Um, do you have any like how Cecilia, are you from 710? Is that your section?
Yes, Professor.
Okay. What time do you start that day and what time do you finish? Like I guess 710 is when you finish, but what time do you start on Friday?
For 4:30 to
4:30.
7:20.
4:30. Okay, so you have only one class, right?
Up
Um,
to we have a 3:30 class up to 4:20
so
laboratory pharma.
uh-huh. So it's from 3:30 basically until 7:30.
7:30. 7:20.
Okay. All right. So it's not too bad. So you got only like 4 hours in college. I was afraid maybe it's like a whole day. So like from the morning or like late morning, early afternoon. So that means for you guys for the section 710, for the tests, you'll have to stay back. Basically, your day will have to be from 3:30 until um, for the tests. We're not going to take 3 hours, obviously, on the day of the tests. The tests will be only about 1 hour and a half maximum. So that means we will start at 7:30 twice a semester, uh, which is week uh, 5 and 9, right? And then the third time, which is the final exam, I'm not really counting that in because you are not going to have any labs on week 14. So the only thing you would have to come to college for is the final exam for this course. Okay, so twice a semester, which is weeks 5 and 9 for midterm 1 and midterm 2, you will have to stay in college from 3:30 until like 9 p.m. basically, the latest. If you finish the test early, you can always leave obviously early. So we'll start at 7:30, and at most it will take us 1 hour and a half. Okay, and then by 9, everybody should be out of that classroom. So that's what we're going to do. Unfortunately, I told you last week that I didn't want to put the. I always try not to put the lectures late on Friday nights, but it's just impossible. Literally every single hour is taken. There's a lot of sections. There's a lot of weird scheduling. So the Friday is the best we can find, and nothing else works. Um, Obviously, we don't want to be doing anything on Saturday, even though I can see some people do have some classes on Saturday. It looks like not too many, but they do. Aloni, we discussed this earlier. It's posted on eCentennial as well. Please double check all the tests, which is three of them will be theoretical tests. That is, will be in person in college. That's why I'm asking people what kind of class they have until 7. So yeah, it's in person in college. You have to be present there. It's a paper, pencil and paper, yeah, test. So we'll leave it at 7. So we'll leave it on Fridays at 7:30 for now. But I still haven't heard from administration about the availability of the rooms because we have to accommodate obviously a lot of people for the exam, and we have to make sure room 203, the big lecture hall, is available on Fridays at 7:30. So once I hear back from them, we will finalize the day and time of the lectures. Okay. Um, I'd imagine again. I'd imagine there are no lectures that late on Friday, but you never know. Considering we have classes on Saturday this term, yeah, probably everything is super busy, the rooms as well. So once I hear back from the administration about the room, we'll make it final. But for now, let's stick to Fridays, 7:30. All right, so that's that. That's that. So going back to today's lecture, as we discussed last week, we will continue the calculations in this lecture. Um, Everything obviously is recorded, will be posted. Those of you who are unable to attend, um, we will pick up from last week's file. This is where we stopped last time. Um, I will go over dilution ratio, dilution factor, all those common calculations involving the two, and then I'll show you the dilution schedule, how you should be approaching dilution schedule when you get that thing in the lab. And then if we have time, which we should, I'll go over the lab, the week 1 lab, the one that you had this week, specifically the calculations, not so much the lab itself. It wasn't that complicated, even though probably pretty busy, but specifically the calculations. Each lab instructor had, I guess, their own way of explaining those calculations. I'll show you the way I usually teach to my students when I'm doing the labs, and that way will be consistent with the way I explain the calculations to you in general. So it will be look at it as a practice, I guess. I'll explain the dilution schedules, and then we will go over a fancy example that the lab was, right? With all those conversions, with all those different cultures that you employed, E. coli and Staph aureus, and so on and so forth. Okay, so there should be a lot of calculations. And then next week, maybe we'll allocate a little bit of time at the start of the lecture for people if they have any questions about the calculations. If not, then we will just start the actual theory in week 3. Okay. Alrighty. So we talked about the dilution ratio last time, and I told you that dilution ratio can be any number, literally any number, as long as it is less than 1. The reason I'm reiterating it so much is because it is a fairly common misconception. A number of students tend to think that a dilution ratio can be only 1 in 10 or 1 in 100. I don't want to say too many of you, but quite a number. Like it's definitely not just an exception to the rule where you have a couple of people, but it's actually a bunch. So again, dilution ratio can be any number as long as it's less than one. Dilution ratio of 1 in 10 and 1 in 100 that you use so commonly is just two examples of the dilution ratio. The reason why people are using 1 in 10 and 1 in 100 so much is only because they're kind of beautiful numbers, you know what I mean? 1 in 10 and 1 in 100. And those are uh, easy ways to dilute the culture quickly, right? And also they can be very easily performed in the lab in terms of you just memorize the two volumes of your culture, 1 ml for 1 in 10 dilution and zero point 0.1 ml for 1 in 100 dilution, and that's it. You just do them automatically, so to say. But that's where the problem comes from. A lot of people somehow, maybe partially because we discussed it with the faculty before, maybe because in food micro in other courses you usually perform 1 in 10 and 1 in 100 dilutions only. Sometimes people tend to think that those are the only two that are possible. It's absolutely not the case. As I was showing here last week, dilution ratio can be 1 in 10, 1 over 4, 1 over 2.4. It could be a decimal in denominator, 1 over 3, 1 over 1.2, 1 over 7.7. It could be also something like 3.4 over 11.7 or 3. Any number really, as long as the whole thing is less than 1. That is critical. Okay. 1 in 100 and 1 in 10 are just very convenient dilutions. Okay. Another way to look at it, to not get confused, dilution ratio basically tells you how much more dilute your concentration becomes as you perform the dilution on your solution. So think about it. If you use this coefficient to describe the level of dilution, um, again, it only proves further that that level of dilution can be any value, and it is determined by how exactly you perform the dilution, what kind of volumes of culture and buffer you mixed together. There's no like preset value for the dilutions. Everything is governed by actual values you have at the bench. Depending on how much you dilute your culture, that's what your dilution ratio is going to be. So if you mix 1 volume of culture and 9 volumes of buffer, you're going to get your favorite 1 in 10. But if you mix something like 3.4 mils of culture and 7.9 mils of buffer, you're going to get something like this, 3.4 over 11.3. And I will explain how I got that 7.9 in a second. So everything depends on the actual volumes you're mixing. Okay. Make sure you understand that. Don't fall into this, false belief that it's only 1 in 10 and 1 in 100. Dilution ratio has to be always less than 1. Just memorize that. And I will show you how we can use this rule to avoid mistakes. So before we talk about dilution factor, which is a very, very similar coefficient to use to describe the dilutions of your solutions. Some people like using dilution factor more. Some people like to use dilution ratio more. In college, it seems like we're using dilution ratio more than the dilution factor, but for the sake of this course and in general for your future, don't get scared. Don't panic when you see dilution factor being employed. I'll show you the difference between the two. It's very easy to memorize. It's very easy to understand as long as you spend a little bit of time kind of wrapping your mind around it. Let's start with the dilution ratio, the one that is familiar to you the most. Speaking of which, by the way, dilution factor, if you ask me, outside of college, in in industry, in scientific publications, I think dilution factor is being employed more often than dilution ratio for whatever reason. So keep that in mind. You're probably going to see dilution factor more often. But anyway, let's get to dilution ratio. We'll discuss that, and then we will talk about dilution factor. So what I'm going to give you is two formula that you absolutely must memorize for the rest of the semester for this course, and I strongly suggest you memorize it for the rest of your life. These are some fundamental formula regarding dilution ratio calculations. And in general, in the calculations that we do in this course, you literally will need to memorize three very simple, very basic formula, three, maybe four, depending on how you look at it. The first formula I gave you last week, I don't even consider this to be a formula because it's just so common to you guys. You've seen it in the school, you've seen it like everywhere. It's the formula, this one here in green, the formula that describes how to calculate the concentration if you have your mass and your volume. So it's super basic. I'm expecting vast majority of students to, remember that formula without even having to memorize it. Okay, so, but let's just, refer to it as our first formula. We're not going to refer to it as first formula. It's just to keep track of how many formula you have to memorize. This is the first one. Again, half a formula, so to say. It's super basic. It's super simple. Most people remember it. So the second formula that I'm going to give you, the next two formula that I'm going to give you is the one that expresses dilution ratio using volumes. Okay, or let's start with concentrations actually. So in order to calculate dilution ratio for your particular step in calculations, for your problem in the lab, you can calculate dilution ratio using two things, two parameters, concentrations and volumes. So let's start with concentration. So the formula looks like this. Dilution ratio equals C, which is the concentration final, divided by C initial. Okay. C final refers to final concentration as the subscript implies. Obviously, it refers to the final concentration of the solution that you are diluting. Okay. Usually when you perform dilutions in the lab, whether it's a culture, whether it's a chemical, you have some sort of initial concentration, right? And then you perform a dilution on that test tube or that flask or whatever. And then you end up getting a final flask, test tube, beaker, whatever you got. So what you start with is your initial concentration. What you end up getting is your final, right? Pretty self-explanatory. I have a question. Okay, zoom in on the doc file. Absolutely. Let's do it this way. Is it better? Let me know. At 190% right now. Let's make it 200. Should be better, right? All right. So concentration you start with is your C initial. The concentration of culture or whatever have you, some sort of chemical before the dilution, before any buffer, before any saline solution or anything has been added to your culture. Final is what you get after completing that step, after the dilution has been performed. So very easy to differentiate, very easy to understand which one is which. So whenever you have this kind of dilution in place, you can always calculate, as long as you know the concentrations, you can calculate dilution ratio for that step right away. And that is calculated as per this formula. Dilution ratio equals C final divided by C initial. Okay. So that's our second formula, major formula that you need to memorize. The third one, this formula also allows you to calculate dilution ratio, but in this case, you will be using volumes instead of concentration. So let's actually put down the formula. So the formula looks very similar to this one, only with the denominator and numerator flipped. It's volume initial divided by volume final. Okay. Now, before I elaborate on this formula a little bit more, on the third one, I guess the question could be, why do we need two formula, or why would you use one formula over the other? So the answer is pretty simple. In some cases, you've seen it in the lab. You've seen it in the lab that you did this week. In some cases, whenever you are looking at a specific dilution step, concentration could be given to you for that step. And you can use this first formula for that. But in some cases, concentration is not given to you. And the concentration is something that you actually have to calculate or you have to figure out. But you will be given volumes for those kind of examples. So depending on which parameters are given to you, you can use either this formula or that one. Okay, so before you employ any of this formula, look carefully at your example, at your problem, and analyze it. Which parameters are given to you, which parameters are not given to you, and I'll show it to you on specific examples later, a little bit later in today's lecture. Okay, so these are the two formula that you absolutely must remember. Copy it into your logbook, like one of the first pages, right after your um, table of contents. Make like a cheat sheet or something with the formula. You're not going to be able to use it for your lab exams, but every other day in a lab, you will have that formula in front of you. There's nothing wrong with that. The more you look at the formula, the more you employ the formula, the faster you will memorize. Alrighty, so these are two formula. Now, a common mistake that students are making, a super common mistake. They kind of remember the formula, kind of, but what they keep confusing is, I guess, let's move this one down for now. They forget, they get confused about how exactly the formula looks like. Is it C final over C initial or C initial over C final? Very common mistake, very common one. So apart from just blindly memorizing this, which you should do anyway, I'll show you a way to remember which one is the correct version, I guess, whether it's C final over C initial or C initial over C final. In order to figure that out, you will need to remember one thing, and it is this statement above here. Dilution ratio is always less than 1. Now, if you remember this, you can analyze your formula. Okay? C final is the concentration of your culture after dilution has taken place, right? C initial is the initial concentration before the dilution took place. So think logically, without even utilizing any numbers, any specific values. Which concentration is going to be higher? Prior to the concentration, the one prior to dilution or the one after dilution? Obviously, dilution by definition is the process of reducing the concentration, process of making the culture or your solution of a chemical less and less concentrated. So that means C final is always going to be smaller than C initial. That follows from the very definition of a dilution process. So if C final is smaller than than C initial, what you're doing in this formula, you're dividing smaller value by bigger value, regardless what kind of values you have. 1 over 10 or 7 over 10 or whatever, 3.4 over 11.1. As long as the top one is smaller than the bottom one, the numerator is smaller than the denominator, you're going to be dividing smaller value by the bigger value. And that means if you divide smaller value by the bigger value, your answer is always going to be less than 1. Less than 1, which is good, which is what dilution should be. Now, if you made a mistake which is again a very common mistake, and you wrote it out like this in your logbook or in your exam, dilution ratio equals C initial over C final. Before you move on, if you're not sure, if you know you make these kind of mistakes often, so analyze your formula before you move on. C initial is the concentration that you start with, is always going to be bigger than the C final, the one that you get after the dilution. So in this case, you will be dividing bigger value by the smaller value, right? And in this case, your answer is always going to be greater than 1. Okay? If you divide 10 by 1, or 100 by 1, or 100 by 50, 100 by 70, it's always going to be greater than 1. And if it's greater than 1, as long as you remember this, the dilution ratio is always less than 1. This formula would be a wrong formula, right? So let's just highlight it. It is wrong formula. Okay. So this way you can always remember that it should be C final over C initial. Smaller by bigger. Now, if you look at the second formula that I gave you, let's talk about that one. Dilution ratio expressed using the volumes. So a very similar logic. The only thing you must remember is, or rather you must understand before you actually memorize it. What is the V initial in this case, and what is V final? As simple as it is, this causes a lot of trouble as well to students. For our applications in microbiological lab, volume initial, I'll even write it out so it's right there in front of you, is always the volume of culture that you are diluting. Okay. Volume initial, let's put it, is the volume of culture you're diluting. Okay. If you're diluting your E. coli, the volume of E. coli that goes into the empty test tube is your volume initial. Okay. If you're performing 1 in 10 dilution, you take 1 ml of your culture, you put it into a buffer, volume of culture is 1 ml. That's your volume initial. Now, volume final is, that's where a lot of mistakes are usually being made by students. Volume final is, as the name suggests, I mean, it's very obvious, but still such a common source of mistakes, is the final volume of your solution, which means volume of culture that you were diluting, right? Staph aureus, E. coli, whatever, or maybe both. Volume of culture plus volume of buffer that you are adding to your dilution. That's where people are making mistakes, forgetting about this part. Let's actually remove bold so it actually stands out. Okay. So volume final is not just the culture. The very common mistake students are making is that they think that the volume final is just the volume of the buffer. Okay. Think about it. You have your culture, E. coli. You're performing a simple 1 in 10 dilution. What do you usually do? You take 1 ml of culture and you take 9 ml of buffer. When you put them together in the same test tube, what's going to happen to your final volume? It's going to be a sum of both volumes, 1 ml and 9 ml. 1 ml of culture, 9 ml of buffer, right? So you must account for that in your calculations. Your volume final in the test tube is always going to be a sum of the culture and the buffer that was used. Not just a buffer. Very common mistake. People think that the final volume is just a buffer. It's culture and buffer. Culture doesn't go anywhere. It doesn't evaporate or anything like that, right? It stays in the test tube, that in the one that you mix everything in. Okay. So as long as you remember that, you can utilize this formula properly. And as per my earlier explanation with this formula, if you look at this one and you forget again which one should it be, volume initial over volume final, or volume final over volume initial, analyze it the way I just explained to you, keeping in mind the dilution ratio has to be always less than 1. So look at this formula. Volume initial is the volume of culture. Volume final is going to be the same volume of culture you're diluting, plus something else, right? Plus some buffer. It doesn't matter how much buffer you add. 1 ml, 10 ml, 70 ml, liter, 5 liters, as long as you add something that is greater than 0, the final volume is always going to be greater than the volume initial. And that means, in this case, you will be doing the same thing. You will be dividing smaller volume by bigger volume. And that will give you the answer that is less than 1. If you, again, made a mistake in your logbook or whatever in your exam, and you wrote it out like this, volume final divided by volume initial, think logically. Volume final is your culture plus buffer. Volume initial is just your culture. So obviously you're dividing bigger volume. I really over-explained this, but trust me, there's no such thing as too much explanation for the calculations. People are still making a lot of mistakes there, usually, as in pretty much always. So Absolutely, I'm trying to over-explain it so that people get the very, you know, I don't know, the very texture of these calculations, where things are coming from. Otherwise, as soon as you see, a little bit more complicated problem, people completely lose track of formula. They completely forget where things are coming from, and they make tons of mistakes. So you must be very comfortable with all these values. You must really understand what they mean. You must be really comfortable kind of playing around with them, spotting the mistakes that you make, and so on and so forth. Only then you will become better at the calculations. So if you uh, put your denominator in the numerator, and if you forget which one is which, analyze it and see that if you divide volume final by volume initial, you're dividing bigger volume by smaller volume. And in this case, you are inevitably getting the answer, whatever the value is. We don't care for the actual absolute value. What we care for in this analysis is just understanding whether this value is smaller than one or greater than one. So if you divide bigger by smaller, you're going to get less greater than one, and obviously it is a mistake. It is a mistake. Okay. So as soon as you see that, as soon as you see that kind of a mistake, you do not continue with your calculations. Everything that you will do after all the calculations you will perform after this mistake will be wrong, and it will only make it worse. So as soon as you find that, stop right there and redo this step, and only then continue the rest of your calculations. Okay. You're obviously using the wrong formula, so how can you continue after that? So that's the way, that's a logical way, if you will, to memorize which of the two formula, which of the two, I guess, possibilities for the formula is the correct one. C final over C initial, or initial over final, and so on and so forth. So hopefully that's clear. One thing is another kind of, a lot of you probably noticed this long time ago, but nevertheless, if you look at these two formula, dilution ratio expressed via the concentrations and through the volumes, you can see that in the one case you have final in numerator, initial in denominator. In the other case, you have initial on top, final at the bottom, right, in denominator. So keep that in mind as well. Sometimes it may come helpful in your analysis, in your calculations. Okay. Now, the next question is, I guess, again, well, I guess I answered that earlier. Why do we need two? Because sometimes you know the concentrations just by the way the problem is formulated for you. You know the concentrations. You may know the concentrations. In some cases, you will not know the concentrations. You will just know the volumes. You can still calculate dilution ratio using these volumes. And then eventually you can actually use um, the dilution ratio calculated through the volumes to calculate the concentrations. I'll show it to you in specific examples. So you'll be using these two formula all the time, using one to help you solve the other one, or the other way around, using the second one to help you solve for one of the values in the first one. I'll show it to you in a second. Another thing actually that I wanted to show you, which is again, only helps you, I guess, get more comfortable with all these concepts. Let's actually let's rewrite both formulas side by side and see what we have. So we got dilution ratio expressed using the concentrations, and dilution ratio expressed using volumes. Now, both formula calculate dilution ratio, right? Just there are two different ways, but equally valid to calculate the dilution ratio. So whenever you're looking at a specific example, specific problem, you can notice that regardless of how you calculate dilution ratio, you're still arriving at the same dilution ratio for that step, whether you use concentration or whether you use the volume. So that means if you have dilution ratio on the left-hand side of both equations being the same thing, which it is for each specific dilution step, you can put the equal sign between both sides of the equation like this. That means C final over C initial equals to volume initial divided by volume final, right? I'm just putting this, putting equal sign between this and that, because both are calculating the same dilution ratio for the same step. Now, if you look at this formula, right, you have C final divided by C initial, and you have volume initial divided by volume final. You can further, I guess, rearrange it this way. Numerator, basic math from whatever grade of the school. Numerator on the left-hand side multiplied by the denominator on the right-hand side. So C final multiplied by volume final equals volume initial, or C initial multiplied by volume initial. That's what you get after rearranging this part. Everybody sees that, right? Now, what does this formula remind you of? Right? I think a lot of people should recognize it. It's the same formula as the way you know it. Yeah,
one.
C1, V1, C2, V2, exactly. So the way you usually know this formula by is C1 multiplied by V1 equals to C2 multiplied by V2. Let's use small, guys. Doesn't matter, small letter or capital letter, still volume, still concentration. Yeah. So what I'm getting at is both of these are the same thing, like C final over V final, C initial over multiplied by volume initial, and C1 V1, C2 V2, the same thing. It's just I like using a final and initial subscripts more than actual ones and twos, because uh, like for me, it doesn't matter. But for students, when you see C1 V1, C2 V2, you sometimes get confused which one is one, which one is two. But if you actually use subscripts that are final and initial, that always refers to specific part of your dilution schedule, right? So initial is the initial one, the final one is the final one, the one after the dilution. So I hope it's less common that you will make a mistake using the final and initial subscripts as opposed to C1 V1. Because what I was seeing before, not too often, but it does happen. It's not so much of an exception to a rule. It does happen. So people sometimes misuse this formula here, and they do their calculations by doing something like that, C2 V1. So they forget which one is C1, which one is V2, and so on and so forth. So they just randomly plug them in. I think it's a little bit easier mentally, I don't know, when you actually put actual meaningful words behind these values. So final is always final. So when you use this formula, look at your dilution schedule. Okay, am I using actually final concentration on the left-hand side or not, right? And it doesn't really matter if you use it as C final, V final, or if you do it like this, C initial. Obviously, I hope that goes without saying. Which part of these values you're going to have on the left-hand side, which ones of them you will have on the right-hand side, doesn't matter. As long as on one side you have all initials for the concentration and the volume, and on the other side you have all finals for the concentrations on the volume. It doesn't obviously matter which one is which. Okay. So that's how that formula is generated, basically, by just understanding what dilution ratio is properly. Okay, so that's that. Somebody else had right. So dilution factor. Let's talk about dilution factor a little bit more. Like I said, dilution factor in college, for whatever reason, we're not using it that much for the calculations, even though in my problems on the exam, you will see dilution factor as well. So I will explain it to you today, and obviously I will be expecting you to know it, how to use it in the calculation. Dilution factor is almost the same thing as dilution ratio, almost. When you see dilution factor, do not freak out. It's nothing. It's not really complicating your calculations by much. Dilution factor, simple formula, is a reciprocal of dilution ratio. That's the formula, as simple as that. A reciprocal means 1 divided by the value. Obviously, if you play around with this equation, you can quickly figure out that dilution ratio is 1 over dilution factor. That's how these two values are related to each other. So what does that mean? That means if you are, for whatever reason, more comfortable, having used it a lot in college, if you're more comfortable with dilution, working with dilution ratio, and if your problem is given to you as a dilution factor, you can always convert, you can stick to dilution factors, or you can convert your dilution factor to dilution ratio. So you can calculate your dilution ratio by dividing one by a dilution factor. So if you want to stick with dilution factor, you can work with dilution factor. It's really up to you. As long as you understand that you have to divide one by the other value to get the other value. Okay. So dilution factor and dilution ratio are reciprocal of each other. But that implies some changes, obviously, some significant changes to this formula. If your dilution factor is 1 over dilution ratio, then if you wanted to express dilution factor using concentrations and volumes, what you would have to do is divide 1 by this formula that I just gave you, right? And everybody should know this basic math. If you divide 1 by a ratio, the ratio is flipped. So the final answer for this ratio is going to be this. Dilution factor is C initial over C final. And the same way, the same logic applies obviously to calculations of dilution factor when you use volumes. You have your volume initial divided by volume final. And again, the ratio is going to flip. You're going to end up having a volume final over volume initial. So both formula for dilution factor are reciprocal of the two formula we used for dilution ratio. For dilution ratio, C final was on top. For dilution factor, C final is in denominator. For dilution ratio, volume initial was on top. For dilution factor, volume initial is again in denominator. And which again is expected because dilution factor is 1 over dilution ratio. And also another major consequence to dilution factor applies to this rule that I gave you earlier about dilution ratio. If dilution ratio is always less than 1, dilution factor is always going to be greater than 1. And that is also supported by the formula that I just gave you at the bottom. That's is always greater than 1. So if you look at this formula, the last part, I guess, the part on the right-hand side, if you divide C initial by C final, C initial is always going to be bigger than C final, right? Because that's the concentration before any buffer was added, before any dilution took place. So you're dividing bigger value by the smaller value, and it's always going to be greater than 1, just like we had it here. For dilution ratio, having it greater than 1 was a mistake. For dilution factor, it is actually a correct value. Dilution factor is greater than 1. Okay. So again, I don't think it's that complicated. It's very logical. This formula is pretty simple, just two values in the formula. It just flips. Well, one thing is for one value, it is on top. For the other one, it's at the bottom. What else I was going to say about these two? Oh, yeah. So one analogy I usually give to students about dilution ratio and dilution factor, which I think visualizes this pretty well. Imagine you have, I don't know, it's not exactly the case, but let's say we have 20 degrees Celsius temperature today. Think the first time when I used this analogy, it was a summer time lecture, and I just stuck to these values for the rest of even in the winter. So let's say today is 20 degrees Celsius. Let's say tomorrow is 40 degrees Celsius. So again, it's an analogy. Don't take it literally, but dilution ratio basically is the coefficient that tells you how much smaller the today's value is compared to tomorrow's value, right? So today's value is 1/2 of tomorrow's value, right? 20 is half of 40. So that's kind of like a dilution ratio. Again, I can't stress this enough. It's just an analogy. Don't use dilution ratio when you talk about temperature. It's an analogy. Dilution factor is kind of, well, it's not kind of, but it's this value tells you how much bigger tomorrow's temperature is compared to today's. So how much is it bigger? It's bigger twofold. It's twice as high. So what I'm getting at is that dilution ratio and dilution factor, they describe the same state, the same physical state, I guess, of the system. You have some sort of initial value and you have some sort of final value. You know what? Maybe the better way to show this would be, let's change this. We'll start with 40 degrees Celsius today and 20 degrees Celsius tomorrow, because this is kind of like concentration, kind of. Again, don't take it in the wrong way. So after dilution, quote unquote, right? Concentration drops, so temperature drops. Dilution ratio becomes shows you how much smaller the value that you got is compared to the value that you had. While dilution factor tells you how much bigger the value that you have is compared to the value that you will get in the future. In the case with our dilutions, it's the value that you get after the dilution will be performed. Okay, but both of these values, they describe the same kind of case, right? Nothing changes about these temperatures. It remains 40 today, remains 20 tomorrow. It's just different way of saying. You can say 40 is double of 20, or you can say 20 is half of 40. That's what literally dilution ratio and dilution factor do in the calculations I guess, in the lab. They just tell you that initial concentration is double or whatever it is, tenfold of what it's going to be after, or you can say that final concentration is one half or one tenth of what it was at the start. Okay, and that's why they're reciprocal of each other. Same logic applies. One divided by 1/2 will give you 2. Or if you take the reciprocal of this quote unquote dilution factor, 1/2 will give you 1/2. That's what we got. Okay. So that's, again, this is just an analogy. Don't take it literally. You do not use dilution ratio or factor to, calculate temperatures. It's just an analogy. I think it's just usually a lot more um, intuitive to people when they see something that is more, you know, more of an everyday experience to them. So that's what the dilution factor and dilution ratio are. So when you face this kind of a problem on the exam, which you will in the tests, read carefully which values are provided to you: dilution ratio, dilution factor. Okay. Uh, if you like dilution ratio better than dilution factor, you can convert the dilution factor into dilution ratio, solve the problem, but then again, carefully read what kind of answer am I expecting from you. Do I expect you to report dilution factor or dilution ratio? So if you solved everything in dilution ratio, and then I'm asking you to give me dilution factor, you just take a dilution ratio, 1 divided by that dilution ratio will give you dilution factor. Just carefully read what the problem is asking. It's not that complicated at all. It's a very simple relationship between the two. So that's that. Any questions so far? We're gonna be moving into there's one more thing I wanted to talk about these values, and then we will take a break, and then we will look at specific dilution schedules, how to solve those using everything that you've been given so far. One more case, the last, not even so much of a case, but in some cases, somebody may ask, what if my dilution ratio is equal to 1? Or if your dilution ratio equals to 1, then your dilution factor is also equal to 1. 1 divided by 1 gives you 1, right? So what is this? What is this case? So very simple. If you don't see it intuitively right away what it means, use the formula. Dilution ratio is C final over C initial, right? And if this whole thing is equal to 1, what does it mean? It means that your C final is exactly equal to C initial. So what does that mean? That means no dilution took place. So your solution was not diluted in any way. Your concentration before the dilution and after the dilution remained the same. So nothing was diluted. Okay. So yes, it's not even a dilution because there was no reduction in concentration, obviously. So math doesn't care, right? For these applications, math just gives you values, but we have to interpret those values based on what kind of scientific field we're using it for. And I'll show you actually how that works in biology, but not in today's lecture. Maybe week 4 or 5, we'll talk about some of those funny things, how math and biology, how math can confuse a biologist, I guess. So that's that. Again, very good point. Who was it? Kyle mentioned. Um, don't forget the very basic definition of a dilution that I talked about last week. This one here, dilution is the process of reducing the concentration of the solution. This means concentration has to drop as a result of a dilution. That's just definition of the process, right? Of the physical process. Why is this important? I'll show it to you right after the break, but we'll be looking at a dilution schedule, at the simple case of a dilution schedule, and I will show you where a lot of students are making a very big mistake because they don't quite understand what dilution is. And partially it's because you were taught this way some time ago. Hopefully it's not the case anymore. I spoke to faculty multiple times about this. Some people were kind of putting that misconception in the students' head, but I think it's not the case anymore. So we'll talk about that after the break. So it's what, 8:25. So let's make a 7 minutes break and come back at 8:32 and we will continue the lecture. Okay, so we'll be back in 7 minutes. All right, so let's get back to the lecture. And for the next part, what I'm going to do is I'm going to share a different file with you. We will put to use everything that we studied so far, and I'll show you how this can be employed when solving the dilution schedule. Okay, so let me share this file here. All right, so this one here is basically a dilution schedule. Um, these are the test tubes. These text boxes is just text boxes for values. Once we get to um, Once we calculate them, I'll place actual values into these text boxes. So you can, if you have a pen and paper, it's up to you, or you can just follow what I do on the slides, or you can draw your own dilution schedule and kind of fill it up as I'm explaining it. It's up to you. Uh, so what we have here is our initial culture that has a certain concentration, and we have to perform a dilution schedule to get to a certain number of colonies on the plate. And as you've done it before, you should know it, you usually asked to plate one target plate or maybe two target plates and a bunch of like two each of the bracket plates, right? Upper bracket and lower bracket. So some of you probably don't have any issues with these kind of problems, but pretty sure a lot of you still struggling with these kind of problems, especially when they get more complicated. So since we're extensively covering calculations in this course, I'll show it to you in all the details. Um, One thing, I guess, which some of you might find different in this course, in my case, quite often, I'm not going to be asking you to achieve just any target value, right? But I'll always ask for you to achieve a specific target value. And quite often it's going to be just 100 colonies on the plate. Okay. Quite often that's the case in science in industry where you aim for a specific value of colonies on the plate, not just any number that falls into the range of the spread plates and pour plates, but a specific value, 100, 200, 150, usually 100. So this problem here, again, oh yeah, zooming in, okay. It might be a little bit tough with this one because there is more content on these ones, on these slides. This should be better. 170, 180. Okay, so you basically have your initial overnight culture. Concentration of this culture is usually known to you. Either prep room tells you in the lab what it is, as it was the case, I guess, for your Staph aureus this week. Or you actually have to figure this concentration out, I'm talking about. You have to figure this concentration out yourself using Macfarlane standards, as it was again the case for E. coli in the lab this week, I'm assuming. Usually is anyway. So you have your initial concentration, and you are told by your instructor, by your manager, whatever, that you have to get 100 colonies on your target plate. So the question is, how do you perform this dilution schedule? So first thing, first things first. Always, especially if you have even slight problems with these calculations, the first thing you should do is you should draw the flow chart. You should draw the actual dilution schedule. Do not neglect the flow chart. All the information will be on this flow chart. It will be very visual when you go over it. It will show you all the steps. If you make a mistake or if you lose yourself in these calculations, the flow chart will help you get back on track. Okay, so always make a flow chart. There's almost always enough time to make a flow chart, so don't neglect it. So we don't know how many test tubes it's going to take us. I mean, I kind of do, I guess. There's a certain number of test tubes, but doesn't matter. Certain number of test tubes. If we need more, we can always add more. If we need less, we can always remove some. So initial concentration, always in your flowchart, put on the flowchart all the values that you are given. Okay. All the concentrations, all the target values, everything that you need to know, put it on the flowchart. So you populate your flowchart so you have as many values as possible. One more thing you should remember, which I think most of you do remember, are the ranges for the spread plates and the pour plates. So when you do the spread plates, you usually are expected to get anywhere between 20 to 200 colonies, and with the pour plates, you usually expected to get anywhere between 30 and 300 colonies. We'll talk about these values a little bit more later in the course, but for now, let's just stick to these values as they are. And the other thing is very important one, quite a few mistakes on the lab midterms and lab exams. People forget about the actual volumes that are required for the spread plates and the pour plates. Spread plates, usually by default, people plate 0.1 ml. For pour plates, usually 1 ml. Again, especially for spread plates, truth is people don't always use 0.1. You can use higher volume. We'll talk about it later. It could be up to 0.25, 0.3 mils for the spread plates, no more than that. But for my problems in the lecture component of the course, if you're provided a problem and the method of plating is indicated as spread plates and no specific volume is given to you for the spread plates, by default, you should assume we're using 0.1 ml spread plates by default. But again, read carefully the problem. Sometimes I might be giving you the problem where the spread plates volume is going to be different from 0.1. Okay. By default, it's 0.1. Same for the pour plates. By default, it's 1 ml. So let's do the simplest, I guess, version of these calculations. Let's just solve for the spread plates with a default volume of 0.1 ml. So one more thing you're missing, you should add to the flowchart. You have your brackets. So put down the values for your upper and lower bracket. Everything again, especially if you're struggling with these calculations, do not neglect this piece of information. Put everything that you know on your flowchart. It will definitely help you. Trust me. Once you get better, you can skip these things. When I solve these problems, I never put anything on any flowcharts, but that doesn't mean that you shouldn't be. Once you get, like I said, once you get better, you'll be doing it differently. But for now, put everything you have, all the information that you have on the flowchart. Now, what else are we missing? There's something else we're missing on the flowchart. Even before we started solving anything, you can actually populate your flowchart quite a bit. One more thing we're missing are the volumes, right? Volumes plated. Since we know that it's spread plates, we know that the volumes plated should be 0.1 ml. So put it all down on the flowchart, 0.1 ml. And I guess we can copy this one. It's going to be also 0.1 for the last lower bracket, so we'll put it here as well. So that's pretty much it. Nothing else is given to us. Everything else will have to be calculated. So let's start the solution. For these kind of problems, what I strongly suggest, always start the solution from the back. From the back end of the dilution schedule where you have the most information provided to you. By the back end, I mean this part here where you are provided the expected number of colonies on the plate, and also you know the volume, right? You have two values here. Whenever you have two values describing a certain dilution step, it's most likely tells you that you can calculate some sort of a third value out of these two. Okay, so let's see what we can do. So I'll guess I'll do it like this. So the first step, starting from the back. Quite often people are, even if they're solving from the back, they start from the target plate. You can start with the target plate. It's not a big deal, but I suggest start with the upper bracket. And I'll show you at the end why this approach is a little bit more convenient. So let's solve our dilution schedule for the upper bracket. Okay. So for the upper bracket, what you know is that you expect to get 1,000 colonies on this plate. Now, where are these 1,000 colonies coming from? They're coming from the test tube, from a test tube that you will have to prepare. You don't know yet what is the concentration in this test tube, but you know that it's coming from some sort of a test tube after a certain number of dilutions, a certain few dilutions, and then you just plate point one and you get 1,000 colonies on the plate. Now, ask yourself logically, if you are getting 1,000 colonies on this plate and you know the volume that was plated, where are all these colonies coming from? They obviously should be coming from this volume, right? They should be coming from this test tube. We assume the plate is sterile. We assume the buffer is sterile, so nothing is contaminated. So all the colonies that you end up getting on this plate, they are originating from the volume that you plated. So the very first thing you do, you calculate the concentration of culture in this test tube from which you plated. I usually call this test tube, let's put it here, um, concentration in the last test tube. In my explanations, I usually refer to this test tube as last test tube. Why is it last? Not because it's last on this list, but because this is the test tube from which you are plating on your plate that you are calculating for right now. Okay. So we are right now looking at only this part of the flow chart. Oops, sorry. For this part, we're looking at this part of the flow chart from start up until here. We don't care for the target colonies for the target plate for the lower plate for now. We're only solving this part up to here, the first three test tubes and the plate. So for us, this test tube is the last test tube in the sequence of dilutions. It's not a big approximations. Don't get confused. You'll see eventually why I'm doing it this way. It's not a big deal. But anyway, let's calculate. Or you know what? Let's actually um, let's call this upper concentration upper bracket test tube, TT test tube, upper bracket test tube. Let's go that way to avoid any confusion. Okay. So again, we know the number of colonies to be expected on this plate. We know the volume that was plated. We know the media and the buffer is sterile. So we can calculate the concentration of culture in this test tube. If 1,000 colonies came from this much volume, what we can do is we can calculate the concentration, right? Upper bracket test tube. What was the basic formula? What was the basic formula? Okay. There's a question. Okay, let's stop here. Alexander has a question. In this example, target colonies are given. How do we know again upper and lower colonies, upper and lower bracket colonies, that is? Also, we are trying to know the dilution schedule based on target colonies. Okay, so let's go back a little bit. So we know the target number of colonies to be expected, 100. How do we know the upper and lower bracket? These things are usually you know them by default. If your target value is 100, your upper bracket should be 10 times higher value than your target. And your lower bracket should be 10 times smaller value than your target. That's why I put down 10 and 1,000 there automatically. So upper bracket and lower bracket are always 10 times more and 10 times less, respectively, than the target value. If the target value was 50, your upper bracket would have been 500, your lower bracket would have been 5. If your target was 200, your upper bracket would have been 2,000, your lower bracket would have been 20. Okay? That's how we know these values. They're always 10 times more, 10 times less. Once we solve this, once I show you the solution, we can talk. Remind me if I forget, I can explain if you don't know why. Let's actually talk about it now. So why do we even need the brackets? So uh, the reason we need the brackets is because we are trying, when we perform the dilution schedule, we're trying to quantify the culture that we have. Uh, we are trying to usually get a very accurate estimate on the culture that we are starting with. Now, whenever you aim for 100 colonies, you can never be 100% certain that you're going to get exactly 100 or close to 100. For that reason, in order to avoid any like uh, meaningless data, people basically set up the brackets. So the brackets are covering a much wider range of colonies than your target is. So if your target calculation is off, you should be able to get somewhere in the good range between your lower and upper brackets. It's like a safe net for your calculations. Okay. Yeah. So we can never expect to get 100 on the target plate. Not even sometimes you can get like 90 and it's good, or 80, it's also good. But sometimes you aim for 100, but you actually get 1,000 on a target plate. So for that reason, you want to cover your upper range and your lower range. That's why people set up lower bracket and upper bracket. Okay. It's like a margin for error. But the values are always 10 times more and 10 times less than your target value. Okay, so now that we got this, again, going back to the calculations, so I suggest start with upper bracket value. Let's just solve starting with the upper bracket for now, and I'll show you at the end why this is a better, you'll see to yourself why is it a better choice. So 1,000 colonies we're aiming for. All of these colonies came from the culture that was plated from this test tube. We assume, I mean, everything is sterile. Everything that should be sterile is sterile, like test tube is not contaminated, plates are sterile, media is sterile, and so on and so forth. Buffer is free of contamination. So all of these colonies are coming from this volume. So what we do is we calculate the concentration in this test tube. And we use a very basic formula, one of the first one actually that I gave you, which was, I told you that everybody should know it. From like school, from mid school or whatever, high school. Mass concentration can be calculated by dividing mass by volume. In our case, in microbiology, we're not dealing with mass, right, in grams and kilograms. Instead of mass, we're using colonies. Colonies is our substitution for mass, right? So you can rewrite this formula as colonies, um, colonies divided. Yeah, that's a problem with this. Colonies divided by volume. Okay. And now just plug in the values. 1,000 CFUs on your plate divided by 0.1 ml. Okay. Get the value. This is going to be 10,000 CFUs per mil. Basic calculations, and last but not least, don't forget the units. You're calculating concentration, you're dividing CFUs by mils, therefore your units are 10,000 CFUs per mil. After that, you're not done yet. Don't forget you're doing scientific calculations. So what you need to do is you have to convert this value to a scientific notation. So that should be 1.0 multiplied by 10 to the power of 4. 10 to the power of 4 CFUs per mil. I need to look up how to actually put on this one here. There we go. 10 to the power of 4 CFUs per mil. Coefficient with 1 decimal, coefficient of 1 with 1 decimal, and then multiply by the CFUs per mil. Okay. So what we just calculated was the concentration in the test tube that corresponds to the upper bracket. So copy all that values in your flowchart into your flowchart. You got a new value, so That's why actually, let's make it smaller. We'll have to make it smaller because otherwise it's not going to fit. Um, so you got a new value. That means you got to place that value on your flowchart. Again, don't forget to populate your flowchart as you get new values, as you calculate new values. Okay. So now we have something to work with. We have the concentration in this test tube that is our upper bracket test tube, the test tube from which we are plating and getting our upper bracket colonies. Okay. So now that we got this value, what we can do is look again at this flowchart, the upper portion of the flowchart. If you look at these three test tubes, could be three, could be five, we don't know. This row of test tubes. For this row of test tubes, we know the initial concentration that was provided to us, or we calculated using the Macfarlane standards. And we also know the concentration of this test tube, some midway into this dilution schedule, right? It's not the first one, this one here, it's not the last one. But what we can do now is we can calculate the dilution, uh, which will connect, I guess, the upper bracket test tube with the initial test tube. So because when you perform the dilution schedule, you have to figure out at the bench level how to get from your initial test tube to your target test tube or upper bracket test tube. Okay. So when I say how to get from one test tube to another, I mean what kind of volumes you have to mix so that your concentration will drop accordingly. So now that you have these two values in place, you can use them and calculate a third value, which in our case is going to be, which value is it going to be? It's going to be dilution ratio. We got concentrations, right? For this part of the flow chart, starting from the initial test tube all the way to this upper bracket test tube, we got initial concentration and we got what will now become a final concentration. This is what we start with. This is what we are ending up with. So we can use the formula that I gave you earlier, C final divided over C initial. Um, hopefully it's not too crowded because I'm zoomed in so much. The text is kind of big. But yeah. So plug in the values. Don't reinvent the wheel. Use the values that you already calculated. Don't forget the units. So final concentration, why is this again? Why is this final concentration? Because we are looking only at this part of the flow chart from here to there. The rest we will figure out later. So our final concentration is this 1.0 multiplied by 10 to the power 4. And our initial concentration is the initial concentration that we started with. 5.0 multiplied by 10 to the power of 5 CFUs per mil. Don't forget the units. Okay, and let's actually let me try moving it to the left. So it looks a little bit. Okay. All right. So simplify this equation, right? Cancel. So what can happen? What you can do is units cancel out. CFUs per mil on top and the bottom cancel out. 10 to the power of 4 gets canceled out, and you end up getting 10 to the power of 1 here, right? Basic math. Everybody should know this from school. How to work with orders of magnitude with powers. So this 4 becomes 1. The whole thing becomes 1. So 4 becomes 0. This becomes 1. So you end up getting 1 divided, 1 in the numerator divided by 5 multiplied by 10 in denominator. 5 becomes 1. So 5 multiplied by 10. Units are gone because units got canceled out. So you got 1 over 5 divided by 10. In other words, 1 over 50. Okay. What I suggest, do not write it down as 1 over 50. keep it as 1 over 5 multiplied by 10. Because if you were to write this down as 1 over 50, there's nothing wrong with that mathematically, obviously, right? You have 5 multiplied by 10 in denominator. We can put the brackets here, so it's a little bit more obvious. So obviously it's 1 over 50. We're not violating any math. But if you were asked, and that's usually going to be the next step at the bench, how to perform this dilution, you wouldn't be able to perform this dilution in the test tube. 1 over 50 dilution is too big of a dilution to perform in the test tube. Okay. I mean, you can use the micropipetter and everything, but it's not a very accurate way. When the dilution is so small, there's always a chance you're going to make a mistake. So what I suggest, keep it as this, 1 over 5 multiplied by 10. And then what you can do is you can further simplify this equation, and you can make it like this, 1 over 5 multiplied by 1 over 10. I split the denominator and the numerator in two steps, in two dilutions, right? Look at this left part, look at this right part, and make sure it's the same value, right? 1 over 50, 1 over 50 on the right-hand side. But here on the right-hand side, what you have is basically two dilution ratio, right, connected with each other to each other by the multiplication sign. So what does that mean in terms of biology, in terms of our calculations in the lab? That means you're performing two dilutions. And how are you performing them? You're performing them serially, one after another. That means in order to perform this 1 in 50 dilution, you have to split it into two dilutions. The first one should have a dilution ratio of 1 over 5, and the second one should have a dilution ratio of 1 over 10. When you combine them, when you perform them serially, your total dilution ratio is going to be 1 over 50, and that is the dilution ratio exactly the dilution ratio that you need to get from this concentration to that concentration. So that's why I have two test tubes here. So for these test tubes symbolize two dilution steps that we're going to be performing. The first one is going to be 1 over 10, 1 over 5. Let's make it 1 over 5. And the second dilution is going to be 1 over 10 here at the bottom. Literally everything that you just calculated, do not invent the values, do not come up with new values that don't exist in your calculations. Okay. 1 in 10, the second one. Okay. So how do you perform now these, the next question, how do we perform these dilutions? I'll actually have to zoom out. It's way too close, up close. So how do we perform these dilutions? 1 in 5 and 1 in 10. Let's make them a little bit bigger. Because again, ultimately you have to go to the bench and you have to perform these dilutions at the bench, right? 1 in 10, usually people know how to perform, right? That's your favorite one. Everybody knows how to do 1 plus 9, right? But 1 in 5, usually what I call the first dilution, is what gives students so much trouble. And that's probably, as in certainly was the case in the lab, I'm sure, because it is every semester. So people don't know how to perform the first dilution, 1 in 5 dilution. So let's look at that step. Dilution ratio of 1 over 5. How do we perform this? Again, there's nothing complicated about these dilutions. Use the second formula that I gave you, volume initial over volume final, right? The second formula, it's a different file from a different, but anyway, you look back at your calculations, dilution ratio, today's lecture, dilution ratio expressed through the concentrations, through the volumes, right? Volume initial over volume final. So you know the dilution ratio for this step. It has been calculated, 1 over 5. And you know the formula that uses volumes. So let's try to solve for these volumes. So let's rewrite it. Volume initial divided by volume final equals to 1 over 5. Okay, we need to figure out the volumes. So the question is, how do we figure out the volumes if we have two unknowns on the left? So we can actually approach this way. Let's keep volume initial. That's our volume of culture. Volume final, though, in denominator is, as I explained it to you earlier in this lecture, the volume final is made up of the volume of culture, which is volume initial, plus volume of buffer. That's what the volume final is. And the whole thing is equal to 1 over 5. Okay? We still have two unknowns on the left-hand side, volume initial and volume of the buffer. But if you look at these, if you look at this ratio, you have a numerator on the left divided by the denominator on the left. And that the whole thing is equal to numerator on the left divided by denominator on the left, on the right, I mean, right? So in order for this ratio to be true, the numerator on the left should be equal to numerator on the right, and denominator on the left should be equal to denominator on the right. To give you an example, if you have an analogy, A divided by B, and that is equal to 1 over 5, a simple solution, even though you have two values on the left or two unknowns on the left, the simple solution to this is A equal to 1, B equals to 5, right? If you plug those values in, everything's going to check out. So we're going to do exactly this with our volumes. In order for this ratio to be true, volume initial, a numerator on the left, that is, has to be equal to 1, because that's what we got on the right. And since we're talking volumes, don't forget the units. Math doesn't care for the units, but we do. And then in order for the denominator to be equal, in order for the ratio to be equal, denominator on the left, which is volume initial plus volume of buffer, should be equal to denominator on the right, which is 5. Now, if the volume initial is 1, and the whole thing here is equal to 5, how much buffer do you need? Volume of buffer equals to 4 mils. Hopefully everybody can see that. Everything got pushed back, pushed at the bottom, but so look at those while I'm moving these plates. Look at those, look at the calculations that I just did, and let me know if you have any questions. So what we did was we calculated the dilution ratio using the concentrations, right? We got the dilution ratio for the first step. It should be equal to 1 over 5. And now we're solving for volumes. Since we actually have to go to the bench and perform these dilutions at the bench using pipettes and the volumes, right? So dilution ratio by itself is not sufficient. We need the volumes. So we use the second formula that I showed to you earlier this lecture, the formula that links dilution ratio with volumes, that calculates volumes, via the calculates dilution ratio through the volumes, using volumes. So we write it down as volume initial over volume final is equal to 1 over 5 because that's our first dilution ratio in our sequence of steps. Now, volume final, as I was explaining to you earlier, is the cumulative volume in the test tube. It's made of the volume of culture and volume of buffer, the ones that you're mixing. So we can rewrite this as volume initial divided by volume initial plus volume of buffer. And again, the whole thing is still equal to 1 over 5. And now in order for this whole ratio on the left to be equal to the ratio on the right, just like, again, let me actually keep this early example here. A over B equals 1 over 5, right? A is your numerator, B is your denominator. What is the simple solution to that? A equals to 1 ml, B equals to 5 ml. And if that's the case, obviously the ratio stands true. And that's what we did. We put volume initial down as 1 milliliter because that's what we got on the right-hand side. And the denominator on the left, volume initial plus volume of buffer, the whole thing, is equal to 5 because that's our denominator on the right. And now we're looking at these two calculations or expressions. If volume initial is 1 ml, volume initial in the second formula is exactly the same volume initial. It's the volume of culture. It doesn't change for our particular step. It's the same culture. So If volume initial is 1, the whole thing is 5. Obviously, the volume of buffer is 4, the difference. So that means in order to perform this dilution, the first one, you go to the bench, you take 1 ml of culture, right? And you mix it with the volume of buffer equal to 4 mils. All of that is performed in the empty test tube, right? You put exactly 4 mils of the buffer, and you put exactly 1 mil of the culture from your original test tube. So we performed that first step. Now, the second step is 1 in 10. How to perform 1 in 10? Everybody knows how to do it. You got to mix 1 plus 9, right? But even for that step, let's actually look at it. So dilution ratio, we'll look at it really quickly. 1 in 10. Everybody knows it. Just remember, you kind of remember it by heart, that it has to be 1 ml of culture and 9 mils of the buffer. But if you try to solve it the way I showed it to you here, you're going to get the same results. Dilution ratio is volume initial divided by volume final, right? That is the same as volume initial divided by volume initial plus volume of buffer. And the whole thing is equal to 1 in 10. Again, numerator on the left, numerator on the right. That means volume initial has to be 1 ml. Volume final has to be 10 mils. And that means, as a consequence of this, volume of buffer has to be 10 minus 1. That is 9 mils. And that's how you mix it, right? 1 plus 9. So the same logic, the same calculation applies for every other case, whether you have 1 in 10 or 1 in 5. Same logic. 1 ml of culture, and then the volume of buffer is your denominator on the right minus your volume of culture. Okay. So here, I'm not going to put it down. For this step, everybody knows how to perform it. It's 1 plus 9. So once we perform both of these steps, we're going to arrive at this test tube with this concentration. And when we plate from this concentration, 10,000 CFUs per mil, if we plate 0.1 ml, we're going to get exactly 1,000 colonies on the plate, right? Again, make sure you understand this step. You have 10,000 CFUs per mil. What does it mean? Always ask yourself if you understand the very basics of these concepts. It means every 1 milliliter of this solution contains 10 to the power of 4, which is 10,000 CFUs. You grab a pipette, you take out, 1 ml from this test tube. That 1 ml will contain 10,000 CFUs. You take another 1 ml, it's going to contain 10,000 CFUs. Another 1 ml, another 10,000. That's what concentration is, right? So if we are plating 0.1 ml from this test tube, what we are doing is we're taking 1/10 of a milliliter, right? If we're taking 1/10 of a milliliter, how many colonies do we expect to have in this volume? 1/10 of what is contained in the whole milliliter, right? So if the whole milliliter is 10,000, 1/10 of that will be 1,000. And that's what we have. That's what we need to get on this plate. So this is how you know that your concentration makes sense according to the volume and as per the expectations on this plate. Okay, everything checks out. Now, we got this upper bracket plate, but we also need, I told you that we also need to get back to the target and the lower bracket. So how do we solve for target and lower bracket? The solution is very simple. Once you have this concentration known, you look at the colonies, right? Expected colonies on these plates. You were expecting 1,000 colonies on this plate. You are expecting 100 colonies on this plate, on the target plate. What's the difference? It's a 10-fold difference. You're expecting 10 times lower colonies on this plate than on that one. The volume that will be plated is the same for both plates. It's 0.1 ml. So what do you think will have to change about this test tube so that you're getting, with the same volume plated, you're getting 10 times fewer colonies that you got here. Obviously, the only parameter that can change is the concentration. So that means that the concentration, I'll just copy paste and change it. The concentration in this test tube, which is going to be our target, let's call it target test tube, should be not 10 to the power of 4, but 10 to the power of 3, 10 times less than this. Why? Because we are expecting 10 times fewer colonies on this plate as compared to that. So we got 10 to the power of 3. Now, how do we get from 10 to the power of 4 to 10 to the power of 3? It's a tenfold difference. The tenfold difference, meaning dilution ratio is equal to 1 over 10. Everybody knows how to perform this kind of a dilution. It's 1 plus 9. Dilution ratio for this step is 1 over 10. Now, before I talk about the lower bracket, it's going to be the same logic, obviously, as you can notice. Why did I tell you to do the upper colonies first, upper bracket first? Because sometimes when you solve for the target first, in your dilution schedule, you skip the upper bracket. You perform 1 in 100 dilution and you go directly from here, from this test tube, into the target, and you skip the upper bracket. But if you solve for upper bracket first, you're never going to skip the target because the target is after it. So once you solve for the upper bracket, for the target plate, all you have to do is just dilute your upper bracket 10 times. Okay? Because the number of colonies in the plates is 10 times smaller for the target than compared to the upper. And it's just by default. That's how it should be. Now, for the lower bracket, it's the same logic. The lower bracket has 10 times fewer colonies than the target plate. You're expecting 100 colonies here, you're expecting 10 colonies here. Volume plated is the same. Volume plated is the same. So where is this difference coming from? Obviously, it comes from the concentration in the test tube. So the concentration in this lower bracket test tube should be 10 times smaller than what we had here. And it should be 10 to the power of 2. Okay. Again, if you're not certain, if you are like, confused or not sure if you got the right value, double check yourself the way I showed it to you with the upper bracket. Look at this value that we got, 10 into the power of 3. Look at the whole step. Does it make sense or not? If you have 10 to the power of 3 CFUs per milliliter in this test tube, and you're plating 0.1 ml from this test tube, how many colonies do you expect to get on the plate? 10 times less, right? Each milliliter has 1,000 colonies. You're plating 1/10 of a milliliter. 1/10 of 1,000 will be 100. And that's what we should get. So everything checks out. Same for this plate. You have 10 into the power of 2 CFUs per mil. So that means every milliliter in this test tube has 100 CFUs. If you plate 0.1 ml, you're expecting to get 10 times smaller number of CFUs on the plate. 100 divided by 10 gives you 10. And that's what we should get. So everything checks out. All the values check out. So that's the simplest case. Well, I mean, a lot of dilution schedules are like that. They're not that complicated most of the time, but this is like the simplest case, the simplest problem. Let's if you have any questions, let me know if you have any questions. Everybody clear on these steps or something is still confusing? Don't be shy, ask away. We are spending all the time today on the calculations, so pose any questions you might have. It's better that you ask them now than you keep them and then you start making mistakes in the exam. Everybody clear with this approach, right? How do we calculate our volumes based on the values? It's just the ratio on the left equals to ratio on the right, meaning that denominator on the left should be equal to denominator on the right. Okay. All right. What we will do next is we will look at uh, this week's lab example. That one was a bit more challenging. There were a lot of extra steps involved, and therefore it took, you know, more calculations, obviously, and more attention, I guess, to details when you go through that dilution schedule, yeah, so that you don't make any mistakes. So I'll show it to you. If we don't have any questions about this one, let's move on. So as far as the lab example, I should have it here at the bottom. Yeah, so let's fix it a little bit. The flow chart that is, and I'll show it to you. One of the ways to approach the problem you were having in the lab. Okay. So the first thing you do, again, whoever was asking, I will have to keep the zoom at this level for this so that we can see the whole picture. I'll zoom in a little bit later once we do the actual calculations here, but for now I want to show the flow chart so that I want people to see the whole thing. All right, so for the problem in the lab, um, there were a lot of steps involved. Um, some of those steps were kind of excessive. Um, and I was the one designing that lab, and a lot of those steps were put in there on purpose, just so that to confuse the students, so to say. Not so much to confuse, obviously, but for you to practice the calculations. Some of those dilutions were not necessarily needed, but you were practicing mixing different culture, calculating according to that, and so on and so forth. So you actually will need this kind of a practice outside of college a lot. So for problems like this, the ones that you had in the lab, whenever there are so many steps involved, again, very important to have a flow chart. Without the flow chart, if you're struggling with these calculations, if you're not seeing the solution, or rather the way for a solution, so to say, right away, you're just going to get lost without the flow chart. So the first thing you do, especially when it's a lab, I mean, you're supposed to prepare for it at home. So at least make a good flow chart at home. Um, Even if you're going to have some sort of a better flow chart, possibly, depending on how your lab instructors are doing it in the lab. But even if you are to have a better flow chart in class, it's absolutely worth putting an effort into creating your own flow chart at home. Because as you prepare the flow chart, you understand the problem better, or at least you may see where you don't understand the problem once you start figuring out the flow chart. So never neglect it. So this is a simplified flow chart of what was happening in the lab. We had, first of all, two sets of cultures. We had Staph aureus and we had E. coli. You had to estimate the concentration of each culture. Staph aureus concentration was provided to you. E. coli, you were using Macpherson standards most likely. Then you had to mix the culture, right? And then you had to uh, perform a set of dilutions, which is, again, we don't know how many dilutions, a set of dilutions, in such a way that when you arrive at this last test tube was being fully dumped into the bottle with 90 ml of the buffer, right? You just took the last test tube and you dumped it into the bottle with 90 mils of the buffer. And from this bottle with contaminated water, water contaminated by two different cultures. You were performing 5 ml and 10 ml membrane filtrations, right? Membrane filtrations, 5 ml and 10 ml. And the problem was asking you, specifically the question had it so that you needed to calculate your dilution schedule in such a way that after all of these steps, right, after you perform your membrane filtration, you are getting 60 CFUs on your filter. I will be solving it for 60 CFUs. You could pick a different number. I think I can't remember now exactly the protocol, but I think I gave you the range between 60 and 100 CFUs. But let's solve for 60 CFUs. That very much could be the question on the exam, where this number, the target number on the plate, is a little bit off. It's not exactly 100, it's not 200, it's just 60. I want to see 60 colonies on the plate, you know? So you have to solve for specifically 60. So um, again, make sure you see the whole picture. You know the initial, the only thing, one more thing that is missing here, let's actually add it here, is the initial concentration of culture. That can always be calculated, obviously, using Macfarlane standards, hemocytometers, and so on and so forth. So C initial is also given to us. So again, I'm going to make up some numbers here and we will solve the whole thing. So we have initial concentration. We have to perform a dilution schedule, but not in a random way, but in such a way that the last test tube, after it's getting dumped into 90 ml of the buffer, when you perform membrane filtration from it, let's say 10 ml membrane filtrations, you're seeing 60 colonies on the plate. So as you can see, everything should be quantified. You cannot just like randomly perform a dilution, because if you perform it randomly, you're unlikely to see this specific number of colonies on the plate. So everything hinges on the fact that you are looking for 60 colonies on this plate. Okay. So how do we approach this kind of a problem? So first of all, before we solve this whole, before we look at it, this whole dilution schedule, a few words has to be said about the culture, because I'm sure that caused some confusion as well. So for the culture, you had E. coli, um, and you had Staph aureus. I believe it was Staph aureus, right? Both cultures had different concentrations. They could have been, depends on the year. Sometimes they're very close to each other. Sometimes they're completely off. So I will, in my example, I will use two values that are completely off. Um, let's say the concentration of E. coli was 1.0 multiplied by 10 to the power of, I don't know, 7. I'm just making up the numbers, right? Those are not the values you had in the lab, most likely. So concentration of E. coli is 1.0 multiplied by 10 to the power of 7. Concentration of Staph aureus, let's say it was, I don't know, 7.0 multiplied by 10 into the power of 8 CFUs per mil. Something like that. CFUs per mil. So the very first step that the protocol was asking you to do was to estimate the concentration of cells, and then you had to dilute the culture with the higher concentration so that it matches the concentration of a lower culture. So what does that mean? You're evening out the concentrations of culture. You start with culture that has different concentrations. You want to bring it down to the same level. That's what that step was about. So what do you do in the lab? You estimate both concentrations and you basically take the concentration, the higher concentration, and you have to reduce it so that the new concentration of Staph aureus is exactly the same as the concentration of E. coli. Again, whether E. coli had higher concentration than Staph aureus or Staph aureus had higher concentration than E. coli for you in the lab, I don't know that. It doesn't matter. We will just assume Staph aureus had higher concentration. The point was to bring this concentration down to exactly the same level as the concentration of your lower culture, the culture that had lower concentration. We're making them equal. That's what we're doing. So how do you do that? In this case, what the protocol is asking you to do is perform a dilution. Okay? Perform a dilution on one of the cultures, not on both cultures, but just on one, because the second culture is already at the base level because it's lower than the first one. So all you have to do is perform a dilution on only one culture, the one that has higher value. Okay? So what I'm showing you here in the lab with this formulation, with this, I guess, with the question being formulated this way. Sometimes you will have to perform a dilution where when the problem is not necessarily calling it a dilution, it will just tell you, please bring the concentration, even out the concentration of cultures you're working with. So what exactly does that mean? That means you have to perform a dilution on the culture that has higher concentration so that it matches the concentration of the lower culture. So if you're performing a dilution, the first thing that should cross your mind is the dilution ratio calculation. How do you calculate this coefficient? Again, what I'm going to show you here on a more advanced example, um, basically everything that I taught you today put into like one place, right? Put together. So as soon as you hear dilution, you calculate dilution ratio. Which dilution ratio formula should you use? Look at what values you got. You got concentrations. So obviously use the formula that makes use of concentrations. So what is that formula? The formula is C final divided by C initial. Now, which one is final, which one is initial in this case? Final is the concentration you are trying to get to, right? In this case, or in our previous example, it's always something that you are trying to get to. So which concentration you're trying to get to? You're trying to get to this concentration, the lower one. So, okay, so put that down, copy it or whatever. Um, so that's our final concentration. Initial concentration obviously is the concentration we start with. In our specific example, it's the concentration of Staph aureus, which happened to be higher than the concentration of E. coli. So plug everything into the formula. Don't reinvent the wheel. Don't make up numbers and values. Just copy everything as is. So you got this ratio now simplified. 10 to the power of 7 cancels out and makes 10 into the power of 8, 10 to the power of 1. So you end up getting 1 divided by 7 multiplied by 10, right? Similar to how we had earlier, 1 divided by 5 multiplied by 10. Keep it in this ratio format. Keep it in this ratio format. Do not make it 1 over 70. Doing 1 over 70 in the lab in one step is going to most likely cause a lot of mistakes. Most likely. Okay, so keep it as 1 over 7 multiplied by 10 and split it into two coefficients, just like I showed it to you earlier with my previous example. 1 over 7 divided by 1 over 10. Double check that nothing changed, so the equal sign still stands. So that means in order to perform this dilution, you have to perform two dilutions, two serial dilutions, back to back, 1 over 7 and 1 over 10. How do you perform these? Step A, dilution ratio of 1 over 7. Use the second formula. So now we have to figure out the volumes, right? We know the dilution ratio. We want to know the volumes now. That's the formula with the volumes. Volume initial divided by the volume final. Or the same thing as volume initial divided by volume initial plus volume of buffer. Same formula that I gave you. You can put the brackets if you want to make it more visual. So it's clearly stating which one is highlighting, which one is the numerator, which one is denominator. If this whole thing, this ratio is equal to 1 over 7, which it is, that means our volume initial should be equal to 1 ml. That's a numerator on the left. And denominator, which is volume final, should be equal to 7 mils, right? Since volume final is made up of the volume initial and volume of the buffer, and we know that the volume initial is 1 ml, that means that volume of buffer should be 6 mils. Oh, no, what is that? Second step, dilution ratio of 1 over 10. So that's our second step, right? Let's highlight them somehow. Our first step in this dilution, our second step. So dilution 1 over 10, everybody knows how to do it. 1 ml, I'm not even going to over explain it. 1 ml plus 9 ml, no, 9 ml of the buffer. So once you have these two calculations in place, again, I'm sure there were a lot of mistakes there. It happens every semester. This dilution that we just calculated has to be performed only on one culture, Staph aureus. because Staph aureus is the one that has higher concentration in my example, and we need to dilute it down to the concentration of E. coli. A common mistake people usually are making in the lab. Oh, we have questions that I haven't seen, sorry. Oh, yeah. Okay. Yeah. We used E. faecalis instead of Staph aureus. Sure. I'm using Staph aureus. E. faecalis it was, obviously. E. coli was a fecal coliform. E. faecalis was a fecal non-coliform, spherical cocci. Um, okay. Yeah. Let's change this. Let's change this to E. faecalis. E. faecalis. And then you use Amendo and Amentero, obviously, for the. So the question, why do we lower the concentration of the ones that is higher than the other? Why can't we do it the other way around? Like the lower concentration, we bring it up. Okay, good question. So the question is, why are we lowering down E. faecalis concentration down to E. coli? Why not do the other way around? Well, first of all, um, you cannot perform a dilution if you want to get from the lower concentration to the higher concentration, right? Think about it. Uh, if you add buffer to your culture, you are diluting it. You're bringing the concentration down. So you will never get your E. coli from 10 to the power of 7 to 10 to the power of 8. Because as soon as you start adding buffer, this concentration will be dropping even more. In order to make this concentration higher, you don't have to perform a dilution. You have to basically just allow the culture to grow more so that it replicates more and so that you have higher concentration at the end, right? But then again, when you start the lab, those are the concentration you got. You don't have time to allow the culture to replicate even further. You just have to start the lab. So you cannot bring the concentration from lower value to upper value. You can only bring it down from the upper value, from the higher value down to the lower value by diluting it. Uh, what you're suggesting is not making a dilution, but actually concentrating the culture. I guess two simple ways to do that would be to, well, not so simple ways, I guess. The simplest way would be to allow the culture to replicate for longer, but that takes time. Or you could somehow remove some water out of that E. coli suspension. But how would you remove water, right? Uh, it's not necessarily easy. Uh, yeah, that's why we bring the higher down. But yeah, that's why we bring the higher value down to smaller value. I'll give you the analogy. Think about it. Um, Imagine you go on a break and you and your friend you buy coffee in college, Timmy's coffee, right? You got regular coffee, one milk, like you got both medium cups, same volume. One got medium coffee, sorry, one got regular coffee, one milk, one sugar. The other one got triple, three milks, three sugars. So if you wanted to bring the concentration uh, of a regular coffee up to the triple, you would have to add two more sugars and two more milks. But in our case, that would imply adding more culture. But how would you add more culture? You need to either have already a more concentrated culture in stock, which we don't. We got what we got, right? This culture was given to us after overnight incubation. Or we somehow have to get rid of buffer in it to evaporate buffer somehow so that the concentration goes up. It's not obviously easy to do. So the easier way is just to take the coffee or in our case, take the culture that has higher concentration and just dilute it down to the concentration of the culture that had lower concentration. Because that can be easily done by adding buffer or saline or whatever have you. Okay. So yeah, so once we do this, we only performed this. You should have performed this only on the culture that had higher concentration. That was E. faecalis. In my example, again, I'm not sure what was in your case. Maybe it was E. coli. Doesn't matter. In my example, it's E. faecalis. Again, a very common mistake that usually students make, they perform this dilution on both cultures. That you don't need to dilute E. coli. E. coli is already good. It's at the lower concentration that we want to keep. Okay. So once you perform these steps, um, your E. coli concentration, let's actually to save time, the concentration of your E. coli will be now equal to the concentration of your E. faecalis, and it will be equal to the same value of 1 over 1.0 multiplied by 10 to the power of 7. Both cultures are um, at the same concentration. Let's actually make this step C. Now, the second step in your protocol told you mix both cultures in 1-to-1 ratio. Very common procedure also in a lot of different applications, mixing things in a certain ratio. Mixing 1-to-1 doesn't necessarily mean that you're mixing 1 ml plus 1 ml. Okay, it could be 1 ml plus 1 ml, but more generally, 1-to-1 ratio means you're mixing equal volumes of substance A and substance B. So for each one part of substance A, you are adding one part of substance B. That one part could be 1 ml, could be 1 kilogram, could be 1 ton, could be, I don't know, 5 kilograms. But as long as both values are the same, or 5 liters and 5 liters, but as long as these volumes are the same, that's what 1-to-1 means. For each one part of chemical A, you're adding one part of chemical B. So here you could be mixing 1 ml plus 1 ml, or you could be mixing 3 mils plus 3 mils as long as the volumes are the same. And one step that was not calculated for you in the protocol, but I think there was a question in the protocol asking you, so what will be the new concentration of your bacterial culture after this mixing? Is it going to be the same or is it going to change? So the catch here is that you're mixing bacterial culture, right? Let's put it this way. So when you're mixing bacterial culture, E. coli and E. faecalis, both at the same concentration, 10 to the power of 7. What do you think is going to happen in this case? Is the concentration going to stay the same or is it going to change? If we're talking about overall bacterial concentration, the concentration will remain the same. 1.0 multiplied by 10 to the power of 7 CFUs per mil bacterial culture. But if we're talking individual cells, specifically the concentration of E. coli, specifically the concentration of E. faecalis, this concentration will drop twofold. Why is it going to drop twofold? Because for E. coli, from E. coli perspective, equal volume of E. faecalis is equal volume of a different culture. They're not the same culture. So that means dilution ratio for both cultures in this case is 1/2. Analogy for you here, think about it. If you're mixing same concentrations of sugar and salt, what do you think is going to happen to the concentration of sugar and salt after? Is it going to be the same or is it going to change? Obviously, it's going to change because if you're mixing 1 ml of sugar, certain concentration, with 1 ml of salt, sugar is not salt, salt is not sugar, right? So sugar serves as a diluent for salt, and salt serves as a diluent for sugar. They're not the same substances. They're not the same chemicals. Yeah, it's going to be a half. Yeah. Okay. So you had to account for that. And after this step, 1-to-1 mixing, the new concentration, let's copy it from here. Again, the values could be different for you, but the logic should be the same. The new concentration of your E. coli and your E. faecalis would have changed to half. In my example, this concentration gets halved, and you end up getting 5.0 multiplied by 10 to the power of 6 CFUs per mil. Everybody sees that, right? Why is it 5.0 multiplied by 10 to the power of 6? That's what the new concentration of cells was going to be. Okay. And now this concentration, right, after you mixed the culture, was the concentration that you had to perform a dilution schedule on and eventually dump the whole thing into the bottle and perform membrane filtration. So for our flow chart, this is the value I'm going to put in there as C initial. Okay. Again, this value could have been definitely should have been different in the lab, obviously, because I'm using made up values, but according to my calculations, that's what the C initial is. Again, what is it? It is individual concentration of both E. coli and E. faecalis prior to the dilution schedule that we are about to start. Okay? So this culture has to be diluted in a certain way, in a very specific way. And eventually this culture gets dumped into the bottle with buffer. And then eventually you perform 10 ml membrane filtration and you get 60 CFUs of each culture on those filters. 60 CFUs on one filter that goes on a Mendo and 60 CFUs on another filter that goes on a Mentoro. Each plate had two filters, two copies. But each of those two should have had 60 CFUs ideally. So how to approach this, we are going to do after the break. So let's make another 7 minutes break, the last one today, and let's come back at 9:50 and wrap up this calculation. Okay, so I'll see you in 7 minutes. All right, guys, we're back for the last half an hour of the lecture. We'll finish at 10:20. So, we got this concentration, um, which is again individual concentration for both cultures. We got it by dividing this number by 2 because we mixed the culture, so the concentration drops twofold. And if you divide this by 2, you're going to get 0.5, 0.5 multiplied by 10 to the power of 7, which is the same as 5.0 multiplied by 10 to the power of 6. This is basic math. If you're not super comfortable with it, make sure you go over it yourself. There's going to be a lot of this kind of calculations in the course, this basic math. All right, so once we have the concentration again, we have to figure out the dilution schedule all as per our flow chart so that we end up getting so many colonies, a specific number, not just any number, specific number on the plate after these steps. So how do you approach this? Same as we did in the simpler example above, we start from the back. We start where we have the most information. At the back, we have expected number of colonies on the plate, and we have the volumes that were plated. So we already have two numbers, two values, and those two values will allow us to calculate a third value. And what is that third value going to be? It's going to be the concentration of culture in the bottle. C concentration in this bottle. Again, why is that the case? All of these cells, all of these CFUs, 60, came from this bottle. We assume the media is sterile. We assume the buffer is sterile. Obviously, all of that is sterile. So they all came from this bottle, and they came specifically, let's just calculate, for 10 ml membrane filtration. So we expect 60 CFUs from 10 ml, and then 5 ml, we would expect 30 CFUs. Obviously, half, right? Because the volume is half. So let's just solve for 6 from 10, 60 CFUs from 10 ml filtration. Now, if you're getting 60 CFUs from 10 mils, right? When you perform the membrane filtration, you pass the liquid, you pass the water through the filter. Everything that is contained culture-wise in the water will get trapped by the filter. It has small pores which trap all the microorganisms. So 60 CFUs came from 10 mils. What we can calculate is the concentration of culture in the bottle, what the concentration should be in the bottle so that we get 60 CFUs after 10 ml membrane filtration. That's the value that should be in there. And that concentration is 60 divided by the, again, don't reinvent the wheel, just plug in the values from the flow chart, right? Divided by 10 mils. And that gives us 6 CFUs per mil. So the concentration in the bottle should be 6 CFUs per mil. If you're not sure, if you still kind of, I don't know, is it actually 6 or is it something else? Double check yourself. Before you move on, double check yourself. How do you do that? Okay, if I have 6 CFUs per mil in this bottle, as I perform membrane filtration with 10 mils of this water, contaminated water, how many CFUs do I expect to get on that filter? So 6 CFUs in every milliliter. So 6 CFUs from 1 mil, 6 CFUs from the second mil, 6 CFUs from third mil, and so on, 10 times like that. So that gives us 6 by 10, 60. And that's what we should get. So everything checks out. So this value is good. So you can move on. All right, so now we know the concentration in the bottle. Okay, we got one more value on the flow chart, which is good. The more values we have, the closer we are to solution. Now we're looking at this specific step. So what I'm doing is I'm solving the flow chart one step at a time. So now we're looking at this particular step, which connects the test tube, the last test tube from which you played it, to the bottle. Okay. For this step, what you know so far is the concentration in the bottle, which we already calculated, expected concentration in the bottle. We know the volume of buffer in the water in the bottle, and there's something else we know that is not here on the flow chart so far. That is that one more value that we know. What is it? It's the volume of culture in this test tube. Volume of test tube is going to be 10 mils, right? Because in your dilution schedule, you prepare all your test tubes to 10 mils, right? So the last test tube is not going to be the exception. The volume in it is going to be 10 mils. We don't know the concentration yet, but we know the volume is 10 mils. And you will be dumping the whole thing, 10 mils, into the bottle, right? So what do you think we can calculate here? This is what I told you earlier. Sometimes you know the concentrations, sometimes you know the volumes. So in this particular step, this one here, you don't know the concentrations. You know one concentration, but you don't know the second concentration. And you don't know the dilution ratio yet. But what you do know are the volumes. So what we know is for that step. So let's mark it as step 4. Let's just don't want to run out of space on this page so it doesn't get too cluttered. Actually, you know what? Let's keep it this way. So for this step, for this step here from the test tube into the bottle, you know that the volume of culture that is going to be added to the volume of buffer in the bottle is 10 mils. Okay. Volume of buffer in the bottle is given to us. It's 90 mils. It's in the protocol. So what can you calculate is volume total. That is going to be 10 mils plus 90 mils. That is 100 mils, obviously, right? And now you know the volume of culture, your diluted culture from this last test tube here. And you know the total volume. So what can you calculate? You can calculate dilution ratio using the volumes, which is volume initial, or in our case, volume of culture, same thing. Volume initial is always the volume of liquid that is getting diluted, volume of culture that is getting diluted, volume of whatever that is getting diluted, okay? And volume final at the denominator, standard formula that I gave you. Volume initial is 10 mils. Volume total is 100 mils. Don't forget it is 100, it's not 90, because you're adding culture to it as well. Don't lose this volume. So it's 10 over 100, and that's obviously 1 in 10. 10 over 100, which is the same as 1 in 10, right? Now, for this step, again, we're still looking at this step, right? From the test tube into the bottle. For this step, we know dilution ratio. We just calculated it, but we also know the concentration in the bottle, right? So for this step, again, make sure you understand it. For this step, when the test tube is getting dumped into the bottle, concentration in the bottle is our final concentration. Concentration of the test tube is our initial concentration. Culture travels from the test tube into the bottle. Its initial concentration, culture's initial concentration, is in the test tube. Culture's final concentration, after the dilution took place, is in the bottle. So concentration in the bottle is our final concentration, and we know it. It's 6 CFUs per mil, and we also know dilution ratio. So we can write it out. We can make use of the first formula, C final divided by C initial. Okay, and in our case, C final is 6 CFUs per mil divided by C initial. We don't know what it is yet. That's our test tube culture concentration, but we know the dilution ratio. It's 1 over 10. Okay. And once you solve for C initial, it will obviously give you 60 CFUs per mil. Everybody sees that, right? So the concentration of culture in the test tube, so C in the test tube, is equal to 60 CFUs per mil. Okay. Again, double check yourself if everything makes sense. Dilution ratio, this was for the dilution ratio, 1 in 10. Dilution ratio for the step is 1 in 10. Why is it 1 in 10? Because we're dropping 10 mils of culture into 90 mils of the buffer. 10 over 100 is 1 in 10. So if we perform 1 in 10 dilution on a culture that has a concentration of 60 CFUs per mil, what are we doing to its concentration? We are reducing it tenfold. So 60 divided by 10 is 6, or 60 multiplied by 1 over 10 is 6. And that's what we had as per calculations earlier. So everything checks out. So this number is good. Okay. If you're confused at this point, ask me. We're about to start the last major calculation. So now we solved for the concentration in this test tube. So now we're looking at this part of the flow chart. Let me highlight it. Oh, it actually worked out perfectly, almost. We're looking at just the dilution schedule. Disregard this arrow. That has been solved already. So we're now looking at only this part of the flow chart from initial concentration in the test tube to the final concentration in the very last test tube. I'll highlight the concentrations we are looking at. We're looking at this concentration and we're looking at that concentration. In other words, we know the initial concentration of culture and we know the final concentration of culture. We have to figure out what should be the dilution schedule that will connect the two. So in other words, how to get from here to there volumes wise, right? So if you are looking at this part of the flowchart and you know and you see that you have your initial concentration and your final concentration given to you, or not necessarily given, but you calculated it, you know it. So what can you calculate right away? You can calculate again a simple dilution ratio using concentrations now. C final divided over C initial. Okay, using that first formula on the dilution ratio. Okay. Again, for this part of the flow chart, we solved everything else. We were done with this bottom part. For this part of the flow chart, this concentration is our initial, this concentration is our final, because now this is the concentration we are trying to get to. Why are we trying to get to this concentration? Is because if we get to this concentration and we perform all of these steps, we're going to get 60 CFUs on the plate. So plug the values in now, the final stretch. So C final is 60 CFUs per mil divided by initial concentration, which was 5.0 10 to the power of 6. 5.0 10 to the power of 6. Don't forget the units. Don't forget the units. So you're dividing using the basic formula. You're dividing the units. You're dividing the C final over C initial. Units cancel out, obviously. Simplify now the values. 60, so you end up dividing 60 by 5.0 multiplied by 10 to the power of 6. I just got rid of the units and nothing else to make it easier. This 10 gets removed, gets canceled out, and you end up getting 6 divided by 5.0. Let's make it just 5 multiplied by 10 to the power of 5. Well, let's actually, you know what? Let's stick to the scientific format. 6.0 multiplied by 5.0, 10 to the power of 5. CFUs per mil already got obviously canceled out, so we're not using them anymore. So why is it 5 here? Because we had a 10 here. This 10 canceled one of the 10s here, so it became 5. Okay, everybody sees that. So what we're doing now is just a set of mathematical conversions, right? By having plugged in the values into our equation, we're just doing a set of calculations and conversion simplifications, mathematical simplifications. So now that's what we got, right? It's a little bit more complicated than what we got earlier, but it's same conceptually, it's the same thing. So let's split this equation or this ratio into two parts, I guess. 6 over 5, right? 6 over 5 multiplied by 1 over 10 to the power of 5. Everybody sees that, right? Six over 5 multiplied by 10 to the power of 5 in denominator. We didn't make any mathematical mistakes, so everything remains the same. Now, let's simplify this further. Let's keep 6 over 5 as is. And let's split 1 over 10 to the power of 5. So this coefficient here, let's split it like this. 1 over 10 to the power of 2 multiplied by 1 over 10 to the power of 2. Hopefully you see what I'm doing here. Multiply by 1 over 10. I split 10 to the power of 5, 1 over 10 to the power of 5 into 3 coefficients. 1 over 100, 1 over 100, and 1 over 10. 2 plus 2 plus 1 gives you 5, and that's what we had here. 6 over 5 is our first constant dilution ratio. 1 over 100 is our second dilution ratio. Another 1 in 100 is our third dilution ratio. And 1 over 10 is our fourth dilution ratio. So we converted this formula into a set of 4 dilution ratio connected by the multiplication sign, which means these are serial dilutions. Everybody knows how to perform 1 in 100, 1 in 100, and 1 in 10 dilution. The only thing remaining is 6 over 5. Now, 6 over 5. So in other words, this is our first dilution, this is our second dilution, this is our third dilution, this is our fourth dilution. So how do we perform the first dilution? The only one that really is unusual to us, 6 over 5. Now, who sees the problem with this dilution? Because the rest of them are super easy, right? Your standard 1 in 100, 1 in 10 dilutions. So 6 over 5, what is the problem with this dilution? 6 is bigger than 5, exactly. 6 is bigger than 5, and therefore this result is going to be greater than 1. And we talked about it, that dilution ratio can never be greater than 1. So what is the problem, right? How is this possible? We did everything right, and then we got the dilution, one of the dilution ratio that is greater than 1. Makes no sense, right? But mathematically speaking, there's nothing wrong with what we just did. But I told you earlier in the lecture today that math doesn't always, obviously, never knows what exactly we're using this language for, right? It doesn't know that for our application, this coefficient cannot be greater than 1. It doesn't make any physical sense. So mathematically speaking, we didn't make any mistake. You can always double check if you're confused or if you're not sure. That wouldn't be a problem. But it's not really a mistake. The reason I picked these values is to get to this value at the end. So what we can do is, since we know that for our application, 6 over 5 dilution ratio makes no sense, what we can do, we can go back to this notation and we can borrow a tan from one of these coefficients, and we can move over a tan from here to there and make it like this: 6 over 50 multiplied by 1 over 10 now instead of 1 over 2. 1 over 10 to the power of 2. We took a 10 from here and moved it over there. So you are ending up with 1 over 10 here. This remains 1 over 100. It's this coefficient. And this remains 1 over 10. Nothing else changes. Okay. So somebody's actually, before we get there, so that's what we end up getting. This is our dilution ratio 1 for the first step. This is our dilution ratio 2. This is our dilution ratio 3. This is our dilution ratio 4. Make sense? Now, 6 over 50 is less than 1, obviously, so that satisfies the requirement for a dilution ratio. We can further simplify this 6 over 50. We can divide it by 2 and make it 3 over 25. And honestly, we can even round it up, right? So 3 over 25, what I did was I divided both sides by 2, right? 6 became 3, 50 became 25. Ratio remains the same, right? For ratio, it doesn't matter. What we can do is we can further simplify this to make this 1 over 8. This is good enough. It's an approximation, but it's a good enough approximation. So let's make it 1 over 8, 1 over 10, 1 over 100, and the last one is 1 over 10 as well. Let's make it a separate line. Let's highlight it. So in order to get what do we have here? In order to get from this concentration to this concentration, you have to perform 4 dilutions. 1, 2, 3, 4. In a serial fashion, obviously, one after another. And this will bring this concentration down to that. So let's put it down. Now for your flow chart, the only thing you have to do is you just have to blindly copy your dilution ratio values from your solution into your flow chart. So the first one should be 1 over 8. The second one should be 1 over 10. Third one should be 1 in 100. And the fourth one should be 1 over 10 again, if I'm not mistaken, right? Okay. And that's literally your flow chart. You can check yourself. Again, don't forget that this was a little bit of an approximation, 1 over 8. But we rounded up, obviously. 6 over 50 is not exactly 1 over 8, but whatever, good enough. Okay. So the only thing that is remaining basically is for you to figure out how to perform 1 in 8 dilution, because everything else is pretty straightforward. 1 in 8 dilution, uh, I hope everybody's comfortable with these by now. In order to perform 1 in 8 dilution, you have to take 1 ml of culture and you have to mix it with 7 mils of buffer. 7, not 8, but 7, because that 7 mils of buffer will also have 1 mil of culture. So it will be 1 divided by 1 plus 7, which is 8. And that's what we have. So this way, you perform this dilution schedule, you will drop this concentration down to 60. After you got this concentration at 60, you perform 1 in 10 dilution by dumping 10 mils of culture in this test tube into the 90 mils of the buffer in the bottle. This will drop the concentration from 60 to 6 tenfold. And then you take this 6 CFUs per mil bottle, you membrane filter 10 mils. Every mil that passes through the filter will contribute 6 CFUs. 6 plus 6 plus 6 plus 6, 10 times, right? And that will give you 60 CFUs on your filter. If you are to perform 5 ml filtration from this bottle, you will get 30 colonies. So the 60 was a calculation for a 10 ml filtration. 5 ml filtration will give us half the colonies, obviously, because it's half the volume. So that's the solution, and that's all the concepts put together. Last thing, somebody was actually mentioning this in chat. Whenever, can't stress this enough, last very important point, whenever you get the dilution ratios like a ratio like this, 1 over 8, or 1 over 2, or 1 over 4, any of them really, do not, I'll put it in bold, do not convert dilution ratio to decimal form. Never do that. Okay? Why is that the case? Mathematically, there's nothing wrong. If you convert 1 over 2 to 0.5, it's still accurate, mathematically speaking. But when you look at dilution ratio as something as 1 over 10, 1 over 2, if you remember the formula involving volumes, you will notice sooner or later, you will get comfortable and you'll be noticing these things, that in order to prepare 1 and 2 dilution, you have to mix 1 ml of culture and 1 ml of buffer. Okay. If you convert this to decimal form, 0.5, again, mathematically speaking, obviously there's no difference between the two, but 0.5 for our application causes a billion mistakes from students. People start mixing 5 mils of culture and 1 ml of buffer, 1 ml of culture and 5 mils of the buffer. Sometimes people get it right and they mix with can be done here. You can mix 5 mils of culture and 5 mils of buffer and make it 5/10, which is the same as 1/2. But that is almost never the case. People start coming up with all sorts of volumes, and they're obviously never correct. So that's why I keep telling, do not convert dilution ratio to decimal form, even though mathematically speaking, it doesn't make any difference. Obviously, 1/2 is the same thing as 0.5, but for our application, ratio format like 1/2 or like 1/10 or like 1/4 is a lot more visual. If you get a little bit comfortable with this formula, a little bit more comfortable with this formula, volume initial divided over volume final, you can always spot the volume of buffer needed when you look at the ratio format. 1/10 is always 1 plus 10 minus 1. That's 9. 1/4 is always 1 plus 4 minus 1, which is 3. But if you were to convert 1/4 into 0.25, which it is mathematically, I can guarantee you, speaking from experience, 95 people out of 100 will not get it right at the bench. Maybe 90 people out of 9 out of 10 people are not going to get it right at the bench. They will be mixing all sorts of volumes except for the correct ones. Okay, so that's why keep it in the ratio format. Um, so Denise, the last question, I guess, Professor, why do we divide the concentration after both cultures have equal concentration upon mixing them in one-to-one mix? So what basically why are we you're asking why this concentration dropped? Where was it? Yeah. Um, no, I think I went way too far. This one here, right? Mixing somewhere here, a mixing step. Blind, can't see it. Where is the mixing step? Mixing right there. Why are we dropping the concentration twofold? Again, we're mixing in one-to-one ratio, meaning we're mixing equal volumes, equal volume of E. faecalis and equal volume of E. coli. Uh, we're mixing equal volumes, but we're mixing equal volumes of different culture. So from E. coli perspective, so think about it this way. Last couple of minutes of your attention. Imagine you're mixing. Imagine you're E. coli, okay, and you're getting mixed with buffer. When pure buffer, when buffer comes in, that buffer is a diluent to you, right? This buffer has no other E. coli culture, so it dilutes you. It drops the concentration twofold. When you mix E. coli with E. faecalis, equal volume, E. faecalis is pretty much a diluent for E. coli as well, because E. faecalis is a completely different culture than E. coli. So from E. coli perspective, from the perspective of E. coli concentration, adding equal volume of E. faecalis or adding equal volume of buffer is the same thing. It's still a dilution because E. faecalis is a different culture than E. coli. It's not the same as, you know what? Let me show you this. Just came up with the idea. So, yeah, this question pops every semester too. So, imagine this is, it's going to be a pain in Microsoft Word. Uh, so let's do it this way. So this is your you have 5, for the sake of the argument, you have 5 E. coli cells, 5 E. coli's in this volume. Okay. And you have, and this volume is one, let's say 1 mil. This volume is 1 mil. You add 1 mil of E. faecalis. Okay. Okay, changing the size. I don't want to change the size of the square, so it's actually visual. I'll have to reduce the size of the font. I'll zoom in a little bit more. So 5 E. coli cells. I'll explain what I'm doing in a second. Hopefully I will. So you have 5 E. coli cells. Let's zoom in some more. You have 5 E. coli cells in this solution. And let's say this volume is 1 mil. What is the concentration of E. coli in this volume? It's C. E. coli is 5 CFUs per mil. Agree? Now you're adding 1 mil of E. faecalis, whatever the concentration. Same, let's say same concentration, 5 CFUs per mil. From E. coli standpoint of view, what is going to be the concentration of E. coli in this joint volume, right? So E. coli concentration is going to be number of cells. It remains 5. E. coli cell count didn't change. You still have 5 CFUs of E. coli. And what is the volume now? It's 1 plus 1. It's 2 mils. It's 5 CFUs per 2 mils. That is the same as 2.5 CFUs per mil. So you had 5 CFUs per mil, and you ended up having 2.5 CFUs per mil. So what happened to the concentration of E. coli? It dropped twofold. Because this volume of E. faecalis or buffer or whatever have you, saline, sugar, salt, whatever, is a diluent for E. coli. E. coli numbers don't change, but the volume doubles. That's why the concentration drops twofold. Make sense? Who was asking? Denise? Yep. Okay. So that's why the volume drops. Sorry, the concentration drops twofold. Yep. Vasima, on the exam, will we have lab calculations? On theoretical test, on midterm 1, 2, and the final exam, you're not going to have specifically lab calculations. But since we're covering calculations in class, you will have a lot of calculations. You will have 10 calculation questions to be specific that are very similar, will be very similar to some of the calculations you're doing in the lab. It's just inevitable. But I'm not going to be specifically asking you calculations like from the lab manual, but they're just going to be calculations in general revolving around dilution schedules and dilution factors and ratio and all that stuff. So that's why we're covering this in the lectures. So yes, as we discussed already last week, as it has in the course outline, your theoretical tests will have 10 calculation questions, not lab, but like practical calculation questions. Calculations related to calculations in the lab, let's put it that way. You will be given the culture, you will have to perform a dilution schedule. You obviously don't have to do it during the exam in theory, but you have to show me you have to do the calculations and pick the right answer. So that's why we're covering this in lectures. Each test will have 10 calculation questions, and they will be worth 2 marks each. Yep. Alrighty, guys, that's it. It's been almost complete 3 hours, 10:23. So let's wrap up with the calculations for today. Next week we'll see if we have any questions about calculations. If we do, I'll spend like maximum half an hour going over it one more time, and just the very basics, and then we will start actual lecture in the first lecture next week. And last question: can I use a clean, sterile tube to get, for example, 1 ml of E. coli and 1 ml of E. faecalis? The adjusted concentration of it, then use the same concentration. Not sure if I'm getting it. So you can use the sterile test tube to get 1 ml of E. coli and 1 ml of E. faecalis of adjusted concentration. Yeah, the one that you reduced. Then use the same concentration. Oh, so if you're mixing the culture, 1 ml plus 1 ml, if you don't adjust the concentration, there will be an error, obviously, because the concentration will drop twofold. I mean, you didn't divide, so you're saying you did not account for the. Well, let's see how many colonies you get on the plates.
Professor,
Yeah,
because in our laboratory, we adjusted the E. coli because the E. faecalis have lower concentration.
yeah, that's fine. That's
So
fine.
we adjusted it to have the same concentration with
Yeah,
we adjusted the E. coli to have the same concentration with E. faecalis. And
Hmm.
then we use a different, so once the E. coli was adjusted, then we collected from that adjusted, like that new stock of concentration for the
Yeah.
E. coli, we
Yep.
collect 1 ml and then 1 ml from the E. faecalis. So we didn't do this divide by,
By two. Yeah.
yeah, so that's the part that I am a little bit confused
Yeah.
because we didn't do this on the laboratory itself.
So yeah, well, I don't know the way it ran for you, but you should have adjusted it because the concentration does drop. Again, I mean, it is a small error. So you would have had, if I were to explain this with my example, instead of 5.0 10 to the power of 6, you would have 1.0 multiplied by 10 to the power of 7. So your concentration is actually twofold lower than what you claim it is. So that means if you use the bigger value for your calculations, you're probably going to get a smaller number on your plate than 60 CFUs. Most likely, that's what you're going to see. So you'll see what happens during the follow-up. Oh, you already had a follow-up, so um, look at the values you got in your follow-up. Okay. But I mean, technically, not technically, but from the math standpoint of view, you must divide the concentration by two because of everything that I just explained, because the concentration does drop for each culture. From E. coli perspective, E. faecalis is a diluent. From E. faecalis perspective, E. coli is a diluent. And this is like a simple representation of this math. 5 CFUs now, whatever, it could be any number, 10 CFU, 5 CFUs, whatever, right? 1,000 CFUs. But the point being is that the volume doubles after you mix the culture in 1-to-1 ratio, the volume doubles, but the number of individual cells, like by individual, I mean specifically E. coli cells or specifically E. faecalis cells, the number of cells doesn't change, right? It's still like 5,000 or whatever, 10,000, whatever have you. So just remember it for the future. It is what it is. You did get smaller values. Somebody's claiming yes, so that's what I would expect because you overestimated the culture, so you over diluted the culture most likely, and you probably did get smaller values as a result. So now you know why you got the smaller values, and that, like I said, that makes sense. It's okay. I mean, you're just remember it for the future. Okay. Alrighty, guys. I don't want to hold you back anymore. It's been already 3 hours, so we can talk about this more next week. So that's going to be it for today. Um, so yeah, and that'll be all, I guess. Yeah. And somebody is still messaging me. They have an issue with watching the video, so I'll reply to you directly. Okay. Alrighty, guys. So have a good night and have a good weekend. I'll talk to you next week.